Okay, so we've got a block of mass m equals 10 kilograms, compresses a spring force constant k equals 4,000 newtons per meter, a distance of 0.2 meters. The entire assembly is on a frictionless platform that is h equals 0.45 meters high. The block is released from rest, and the spring reaches the natural length just as the block reaches the edge of the table. So the spring pushes, and then the spring is uncompressed and expanded at this point when the block is off the table. So let's put in some bar charts here to figure out where is this energy before the release. So it's compressed. So we definitely have spring potential energy, and it's at a height above the ground, so we definitely have gravitational potential energy. Do we have any kinetic energy? No, it says we're released from rest. So we just want to show the types of energy. So gravitational potential energy, I'm going to say there's 5 units there. Spring potential energy, I'll say there's 5 units again, so that way the total adds up to 10. And then we can watch how the energy transforms through these bar charts. At the edge of the table, do we have spring potential energy? Nope. That spring potential energy is gone and is now into the block. All of that spring potential energy has been transferred to the block as kinetic energy. What about gravitational potential energy? Do we have any? Yes, we have not changed heights, so we have not changed gravitational potential energies. So there's that. Then we have when it reaches the floor, just before it hits the floor. Do we have any gravitational potential energy? Do we have any spring potential energy? So that means all of our energy lies in kinetic energy. All 10 units or whatever. That. It's just a bar chart to show where the energy is at different times. Part A says calculate the block's speed at the edge of the table. Now that we've looked at the bar charts, and we have these here for reference, we can calculate the block's speed at the edge of the table using whatever energies we have in the beginning and set them equal to the energies that we have at the end. In the very beginning, we have gravitational potential energy and we have spring potential energy. And in the end, we have kinetic energy and we have gravitational potential energy. Oh, we've got gravitational potential energy on both sides of this equation. So guess what that means? They cancel out. So what we're left over with is 1/2 kx squared equals 1/2 mv squared. Remember, we're solving for v. I'm going to take this and I'm going to continue my work over here. So we have 1/2 kx squared equals 1/2 mv squared. My 1/2s will cancel out. And what I'm left with is kx squared equals mv squared. Divide by m on each side to get v all by itself, and I get v equals the square root of kx squared over m. However you want to handle that x squared under the radical is up to you. I'm going to just keep it and then plug in my numbers. I think that just helps me. So when I do that, I get k is 4,000 times my x squared, 0.2, is going to be equal to 0.04 divided by my mass, which is 10. And that gives me a velocity of 4 meters per second. Calculate the block's speed just before striking the ground. Just before striking the floor. So that's this one. So all of our energies in the beginning equal all of our energies in the end. Where do you want to say the beginning is? Do you want to say it's the edge of the table? You could. Do you want to say it's the beginning when the spring is compressed? You could. Doesn't matter. It's up to you because this system is not having any work done by outside forces. So all of the energy that's in this system is staying within the system. So that means we can make our starting point and ending point wherever we want. For you guys, I'm going to say the starting point is here and the ending point is here. That means I don't care what's happening in the middle. I only care about what happened in the beginning and what happened in the end. Just like on a roller coaster. If we have a roller coaster that does all this, and it started from this line, and then we have a roller coaster that does this, well, which one is going faster at the end? They're both going the same speed. It doesn't matter what you're doing in between. You're looking at this change in gravitational potential energy from here to here, from here to here. So it doesn't matter how you get there. It just matters where you are when we're talking about energy, especially gravitational potential energy. All right, so in the beginning we have gravitational potential energy and we have spring potential energy, and in the end all of that equals to kinetic energy. So we have mgh, and 10 times 10 times h is 0.45, which will just give us 45. And then we have the spring potential energy, 1/2 kx squared. So k is 4,000, half of that is 2,000, times x squared, and that equals 80, equals 1/2 mv squared. Now my next step, I'm going to bring down here in blue. This was A, this is going to be B. So I am going to multiply, I'm just going to multiply by 2 and then divide by m from each side. Don't forget your squared. That means we got to take square root of all of that. So all of this junk right here equals 25, and we take the square root of 25, and we will get V equals 5 meters per second. Just before it hits the floor. Now let's calculate the horizontal distance the block travels as a projectile. Projectile, Mr. Scopetis, come on! Well, remember, it's calculating the horizontal distance. So we can use our range formula, which is the initial velocity in the x times t. Okay, so how are we going to get the initial velocity in the x? When it becomes a projectile, we are launched horizontally already. So our launch angle is 0, which means all of our velocity, all of the launch velocity, is going to be the initial velocity in the x. There is no vertical velocity yet. So initial velocity in the x, that's going to be this right here, which is 4 times t. Uh-oh. We don't have t. We don't have t. We're going to go to our y equations. Y equals 1/2 gt squared. Solve for t. And we get t equals 2y over g inside the radical. 2 times y is going to be 0.9 divided by 10. So our time is going to be equal to 0.3 seconds. Now we can take that, plug it in here to get our displacement. 4 times 0.3 is going to equal 1.2 meters. Last one, if the block strikes the floor and does not bounce but the floor is frictionless, how much energy is lost with the impact with the floor? Explain how you arrived at your answer. I want to properly go through this. I was going to try to rush it in, but I'll just make a sequel to this episode for you.